the story I would like to quickly talk with you about is about handedness-related difference in the corpus callosum, a topic I'm dealing with since my PhD. But it was triggered that I wanted to look at it again because I found some studies which simply assumed that left-handers have a bigger corpus callosum, and this has obviously to do with some literature that was published in influential journals, like you hopefully can see if I can change the slide. Here, a science paper from 1985 most likely kickstarted this all by Sandra Whittleson, who found, if you believe the title, the corpus callosum is larger in left-handers. There's already the first little problem here. She actually didn't look at left-handers. She actually didn't have any left-handers, or not many left-handers in a sample. She rather compared consistent right-handers with mixed-handers. So she made groups of individuals which consistently use the right hand for the tasks she asked the participants for in the ANET questionnaire, and then followed ANET's definition of consistent versus mixed-handedness in her distinction. And she did postmortem studies on the brain of diseased cancer patients, in which she, as you can see on the picture in the upper left, tried to measure the corpus callosum in its entirety and also looking at subregions. And on the right, you can see the findings. The total corpus callosum was significantly larger in the mixed-handers, basically across all areas, except for the posterior fifth, which would be here the splenium. And if you just look at the total corpus callosum, the effect size is actually quite large, with a Cohen's d of 0.85. So the mixed-handers had about 11% larger corpus callosum. She then tried to do some more studies on that by extending the samples, more or less confirming the whole story, but the effects got a bit smaller over the time, but the general story stayed with us in a way that the mixed-handed have the larger corpus callosum. From that, two things evolved. She made a theory from this, which some of you might remember, that mixed-handed have a bigger corpus callosum because they are bilateral organized, and as a result, you need to have more communication between the hemispheres, while consistent handedness would be related to smaller corpus callosum, and because you can have this on one hemisphere being dominant for the task. And she extended this towards all types of laterality, so there would be a nice theory on how to relate corpus callosum size to brain asymmetry on a functional level. Another thing which was derived from that is that cognitive neuroscientists seem to remember one take-home message from this paper, and that was left-handers, maybe mixed-handers, have a larger corpus callosum. And as a result, people nowadays still cite this paper, right? So I have two examples here, and maybe you have done this as well, and I guess I would also have done this if I wouldn't have deeper looked into that. In principle, these papers use handedness as a proxy for corpus callosum size. Give you one example here, maybe from the right. I don't read this now all to you, also for lack of time. So here the idea that left-handers have a larger corpus callosum, citing the Whittleson paper and Alan Beaton's review article. This may foster interhemispheric connectivity and bihemispheric representation in cognitive function, with positive effects for left-handed individuals' intellectual skills, such as verbal reasoning and verbal fluency, episodic memory, and so on. Right? So the bigger corpus callosum in left-handers makes these individuals smarter in many tasks. So this that's how this finding nowadays is still used, although none of these studies which use it actually measure the corpus callosum. Yeah, this was the premise where I thought, okay, let's do a meta-analysis, and this meta-analysis did together with Marietta, published this year, and the effect basically was null. If you look at the forest plot here of all studies which compared consistent right-handers with mixed-handers, then you see that the Whittleson paper is almost an outlier in as much as it is not even in the prediction interval of the meta-analysis. In this paper, we discuss why this could be the case, but in principle, the effect is actually zero. There's no effect in the data that holds this idea, right? So this is problematic. But now we could actually stop here and say, okay, there is no effect. But we also found in the meta-analysis a couple of things which we couldn't answer with the meta-analysis alone because the data published was not enough. And these are the 4 of these points, which I would like to quickly address here. So these studies used different definitions of what consistent hand preference is. Some used Wittelson's original approach by basically qualitatively looking at each item. I will come to this in a sec. And others just used a high laterality index to, for instance, the laterality index of 80 to split off consistent from non-consistent handedness. Then subregional differences are an issue, which we addressed partially in the meta-analysis, but the original study usually used some kind of geometric subdivision of the corpus callosum, which might be seen artificial and maybe also not very sensitive to fine differences. So a bit more fine-grained analysis could be possible. And they ignored the microstructural variability. So the corpus callosum obviously is composed of axons which could differ in myelination, and here diffusion imaging could give some information. There are a couple of studies out there, but there weren't enough to do a proper meta-analysis with it. And finally, brain size we couldn't include in the meta-analysis in a good way, again, because there weren't many papers which actually used brain size in a reasonable way to correct for difference in brain size into corpus callosum size. Brain size and corpus callosum size are well correlated, as one might imagine. So it's usually 0.3 or more. So what we did, and after the meta-analysis basically was looking at the Human Connectome project, extracting the data. The Human Connectome project has the advantage that they use a version of the Edinburgh Handedness inventory and have a large amount of participants in the sample so that we actually can expect a good amount of or a good distribution of the handedness score. So it's not pre-selected in a way for handedness. So one can expect 10% should be left-handed at least. So that's what we did. We looked first at does the different definitions of consistent hand preference differ or make the difference in analyzing the corpus callosum. So to contrast these two once more, so Wittelson did a qualitative definition. So she said consistent right-handed preference are individuals which on all items score right, or some maybe either preference, but it should be no left-hand preference of any on the items, right? So she did an item-wise analysis. And a quantitative approach was, for instance, used by one of the first replication studies by Habib, which simply set a laterality quotient of 0.80 or of 8 plus 80 to define consistent right-handers versus mixed handers. The 0.80 was arbitrary, although this is usually the median value when you look at the handedness score as at the distribution. And if you do this for the Human Connectome project, where there's 1057 data sets from which we could extract the corpus callosum, then you see this distribution and you say, oh wait, they look very, very similar, wonderfully. You shouldn't do a cross-step though, because they actually result in a significant amount of individuals being differently classified in the two approaches. So these off-diagonals that I made red here are individuals which are differently classified by the two approaches. And you see this amounts actually to 277 or 26% of the sample. So the first thing we did was doing the analysis of the corpus callosum, again, by splitting this by analyzing the corpus callosum once using the quantitative and once using the qualitative definition to see simply if there is a difference. And this is the data. So we have here 3 dependent variables. So one absolute area by putting forebrain volume as covariate in there, or using a relative area, meaning dividing the area by the size of the brain, by the forebrain volume. And qualitative would be the Wittelsson approach, quantitative would be the Habib approach, you see here the means, they're already very similar in all these outcome variables. And you see that on average, the effect size is very, very small. And here also the confidence intervals are very narrow, suggesting that there's no effect under 0.20 Cohen's d between them. If you want to know more exactly how we extracted the corpus callosum, please check out Nora's poster. She will present this tomorrow. So she will also show you then, potentially describe you how we exactly extracted the data. So one could conclude from that, well, consistent hand preference, no matter how you define it, seems not to result in difference in the corpus callosum size. But I was also a bit curious because I said fishing expedition was my title, right? So what can we do to find the difference? So I decided to simply make a loop by defining consistent hand difference based on the Heidenberg handedness inventory, just using the absolute value. So that would be the consistent left-handers. The few that are there would fall into the same category as the consistent right-handers, and then compare the consistent handed with the mixed handed or non-consistent handed, depending on where I set the threshold. To walk you through this, 0.80 would be what was used in the example before, right? Which divides this group in 667 consistent versus, so mostly right consistent individuals versus 390 mixed individuals. But you could also increase the threshold or lower the threshold, right? And here's the data for this, the Cohen's d for the comparison, depending on where you set the threshold. And the green bands are the confidence intervals for this comparison. And you see it is basically going around 0. So no matter which laterality index you use, there's to separate these groups, there's no difference left. There's no real difference between the groups. Yes, obviously when I have the threshold that low, set that this low, then we can't talk of consistency anymore because these are mixed handed. But this is just to prove a concept, right? That there is, no matter how one defines it by the laterality index, there's no effect. Then looking at the sub-regional areas, so Wittelsson did sub-regional analysis. This is from the 89 paper, which extended the total sample. You see the total area difference between the handedness groups has changed. So it's not as large anymore. So the significance is just reached. But now the isthmus was the area which showed up to be still significant, and some other areas as well. So we see this on this graph where this would be round about. But the problem with these definitions is that the geometric definition simply counted just for variability in the corpus callosum, which is huge, as Nele also said earlier today. So one has to be a bit careful there. But so alternative approach is to analyze the corpus callosum thickness, as Rene did. Let's read it. And Nele, sorry. And you see one can do this with more measures than 5. One can do this with 60 in this case, but in this study we did this with 100. So for each corpus callosum, simply defining 100 segments thickness measures along the midline of the corpus callosum. Right? So this is more or less automatized done, and it's measured orthogonal to this midline. And here, without much here's the effect size map of these comparisons, again using the Wittelsson approach and the Habib approach, just to show the sample sizes once more. And if there was something significant, it would pop out, but there is nothing significant across the entire corpus callosum. We did, you see, for absolute thickness, but also when you use covariate of brain size or relative thickness. We obviously did FDR correction for multiple comparisons, but even if you ignore this, these are the maximum effect sizes that are in the study along the entire corpus callosum. And you see that the confidence interval here in this case actually includes the 0 also when you are not correcting for multiple comparisons. So right, this would be significant. There's not significant on a unadjusted level, uncorrected p levels. Here, this is maybe a bit outside, but when the effect is still small. Here, it would be significant, but as said, it doesn't survive the multiple comparison correction, and you see the effect sizes are still not enormous. So from this one, might maybe say that regional difference might be also not the case here, that they are relevant in this setting. Then finally, then we are almost at the end, diffusion analysis. Some studies like this one, published in the wonderful Journal of Laterality, compared right and left-handers, in this case, just by direction of handedness compared, and using a so-called PBSS analysis of fractional anisotropy. We see they found some difference in the corpus callosum, which was significant. So it might be worth looking into this. And this is now, again, data from the Human Connectome project, did this analysis, did do this voxels of the corpus callosum in M&I space. If you want to have details, we can talk about this at one point. But in general, the same finding, the FA analysis also doesn't find any differences. Again, I plot the biggest effects in either direction, so bigger in left or in right-handers. And correcting for brain size. So all in all, the fishing was not successful in finding any differences comparing consistent droid with mixed handed. So I would conclude that there's not really much of a difference between the two groups, and substantial difference, I put this in quotation marks because it's a bit difficult to define what is a substantial difference when it comes to brain anatomy, because we actually don't have a good relationship between how a couple of millimeter bigger structure relates to function. Without this, studies like Neles would show this, for instance, right? That the bigger corpus callosum helps here, and we could make some correlation. But as long as these are not fully established, it's difficult to judge what is a big effect size or not. But in general, they are comparatively small. Not shown here, I also did the analysis comparing the dominant right-handed with dominant left-handed, so just taking the split at 0 in the laterality index, or comparing the consistent with the consistent right with the consistent left-handed, but also there were no effects in any of these analyses that are remarkable. Although one has to say that for the consistent left-handed, there's very small sample. I think it's 36 in the Human Connectome project. So it's very difficult to have narrow confidence bands. So the effect size we can exclude are relatively large. Not analyzed, I haven't looked at handedness defined by performance, which has basically to do with the fact that the HCP measures have a really, really low reliability, and I didn't see the point in making groups or any analysis related to the performance measures if the reliability is under 60, or even worse, I think 0.40 or so for one of the measures. So please, and this is the take-home message, and then I'm actually done, stop inferring difference in callosal connectivity from hand preference if you do not measure the corpus callosum in the future. Please don't. And with that, I would like to thank you for your attention, and hope you have a good time in Bergen in general. But if you have questions and Marco allows, or Carsten allows to, I'm happy to take them, obviously.
Thank you very much. I think everyone received your take-home message. Any questions, comments? They're all straight by your message. Everyone voted down.
I can live with it. It's good for the schedule, is it?
Yeah. Sorry to ask a question about sex, but it would be, you often hear that females have better connectivity between the two sides. So did you look at, well, I mean, I guess you could look at that, and do you believe there's a sex difference in relative callosum size?
Yes, to both. It was one effect in the analysis, but I didn't present it now for brevity. But obviously there is a sex effect. So if you look at the absolute corpus callosum, the male corpus callosum is bigger simply because the male brain is bigger, and that explains a lot of variance. The moment you correct for brain size, the effect goes down to about 1% explained variance or below. And there's a bit of a, since this is such a small effect, some find it, some don't find it. I would say there is a small difference in favor of women, so that women have a relatively bigger corpus callosum. But maybe one should, there again, 1% explained variance or below doesn't sound much, but as long as we don't have a model of how 1% explained variance relates to cognition or any other performance, it's very difficult to say, does it matter? In general, I would say if something like the corpus callosum, which is obviously relevant for a lot of tasks and maybe used tons of times during me talking right now and trying to communicate with you, it might maybe differ that my corpus callosum is a bit smaller compared to female corpus callosum. But as said, in the effects are small and one has to think about that. Did this answer the question?
Yes, hi, Patrick here.
Hi, Patrick.
Thanks so much for presenting this result. I'm really happy that this is out now. I'm wondering, what do you think is then the neural foundation of correlated handedness? Because as you know, it might also not be in local asymmetries in some regions or anything like that. So do you have any idea what might be the neural determinant?
I don't have an idea, but I share your curiosity in a way. But I mean, why? The question is, why need to do? Why should there be differences necessarily? The brain could still do the same task if it doesn't really differ much, right? It's just the other hand or so. I don't know.
Yeah, that's right. But I was more wondering about like what you might think is then the neural structural, not difference, but determinant of handedness. So do you think there is something like that? Do you think we find the neural foundation?
Maybe on a more, maybe not with imaging right away. Maybe we have to look a bit deeper than imaging. So standard imaging, I mean, volumes of cortex or so might not be sensitive enough. You can also talk to James about it, who you obviously know, who will present later tonight. And he also looked at handedness effects on cortical asymmetries, and he hardly finds anything, right? So, and the effect sizes are very small when you have something.
Thank you. I just have one really quick question. In terms of Bianca here, in terms of callosal size, can you infer interhemispheric connectivity with larger callosal size, or is that something that's not really established?
Yes and no. I mean, there's variability on a substructural level as well, or sub-measurable level as well. But there are a lot of studies which relate the axon count in a region to the thickness of the region, for instance. And they find usually a linear correlation between positive correlation between the number of axons in the corpus callosum and the size of the corpus callosum. So we can somehow assume that this is a good measure of interhemispheric connectivity on a structural. Yeah. It's not perfect because it can be differently spaced. Myelin might differ, right? So if you have a lot of axons which are low myelinated versus a few axons which are more myelinated, you have maybe a different functioning going on. But in principle, it's a predictor of the bigger, the more connections you're having on an axon level.
Hi, Rene, we're missing you here. Marcus here. Hi.
Hi.
My question refers also to, group differences, whether it's sex or whether it's handedness. I'm still surprised that people still look at so rough structural measures, like the size of the corpus callosum, or even if you divide it into all the subdivisions. We should surely look at the cells, densities, so measures that MRI might not necessarily be able to fit the answer to.
Yeah, yes, I agree to some extent. Obviously, that's the measures we are having, right? So the moment we want to do cell measures, I think we can't do research in humans anymore, or only limited. I don't want to be so negative. I mean, there are certainly some structure-function associations we can find, but we need to be careful that we don't follow a couple of studies which had a small sample size and large effect size, like the Wittson study. So the question is, what does hold if one does a meta-analysis or it has bigger sample sizes? Again, bigger sample sizes means we get everything significant eventually, statistically. So we have to question from what effect size we are actually thinking it matters. And this is not easy.
Okay, thank you very much.
Thank you, and enjoy the rest.